The Square Kilometre Array, SKA, represents one of the most ambitious scientific projects of the 21st century, aimed at building the largest and most sensitive radio telescope in the world. This international project involves numerous countries and scientific institutions with the goal of exploring the universe with unprecedented precision, opening new frontiers in cosmological knowledge and fundamental physics. The idea of the SKA began to take shape in the 1990s when the international astronomical community recognized the need for an instrument capable of overcoming the limitations of existing radio telescopes. The vision was to create a radio telescope with a total collecting area of 1 square kilometer, hence the name Square Kilometre Array. This would allow scientists to address fundamental questions about the formation and evolution of the universe, the nature of dark matter and dark energy, and the possibility of extraterrestrial life. Furthermore, the SKA will enable testing of advanced physics theories, such as general relativity and quantum gravity. The main motivations driving the realization of this project include 1. Limits of current radio telescopes. Existing instruments are not sensitive enough to detect the faintest signals from the early stages of the universe. 2. Need for greater precision. Detailed observation of the distribution of neutral hydrogen and other cosmic phenomena requires a much larger scale telescope array. 3. Advancements in data technology. The development of supercomputers and artificial intelligence techniques now makes it possible to manage enormous amounts of data, enabling an ambitious project like the SKA. 4. Exploration of gravitational waves. Observations of pulsars with extreme precision could provide new evidence of relativity theory and primordial gravitational waves. The SKA will consist of 2 main arrays located on 2 continents, a strategic choice to minimize radio pollution and maximize observational coverage. SKA-LO. This array, located in Western Australia, will consist of over 131,072 low-frequency antennas, similar to large TV antennas. It will operate in a frequency range between 50 MHz and 350 MHz, allowing the study of the early stages of the universe, including the Dark Age period, the epoch immediately following the Big Bang. SKA-MID, located in the Karoo Desert in South Africa, this array will consist of 197 parabolic antennas, each with a diameter of 15 meters. It will cover frequencies from 350 MHz to 15.4 GHz. Enabling detailed observations of galaxies, pulsars, and other celestial objects. The locations of these facilities were chosen based on the need for environments with extremely low radio pollution, far from artificial interference, to ensure superior observation quality. The SKA is designed to address a wide range of major scientific topics, cosmology and dark matter. By mapping the distribution of neutral hydrogen in the primordial universe, the SKA will help understand the large-scale structure of the cosmos and the nature of dark matter. Study of pulsars and gravitational waves. By monitoring pulsar signals with extreme precision, the SKA will test gravity theories and could detect gravitational waves through variations in signal arrival times. Star and galaxy formation. By observing star-forming regions and distant galaxies, the SKA will provide crucial information on the processes driving the birth and evolution of stars and galaxies. Search for extraterrestrial life. Thanks to its extreme sensitivity, the SKA will be able to detect potential artificial signals from advanced civilizations, expanding possibilities in the search for extraterrestrial intelligence. Fundamental physics. The SKA will test alternative theories to general relativity and could provide new clues about the nature of dark energy, one of the greatest mysteries in modern physics. The realization of the SKA presents several engineering and technological challenges, including data management. The SKA will generate a daily data volume exceeding 600 petabytes, an enormous amount requiring advanced processing and storage infrastructures. Network infrastructure. Transmitting data from the antennas to processing centers will require networks with extremely high capacity, capable of handling hundreds of terabits per second. Antenna design. The antennas must be highly sensitive and capable of operating over a wide frequency spectrum while maintaining manageable costs and complexity. Data processing and analysis. The use of artificial intelligence and advanced algorithms will be essential to manage, filter, and interpret the vast amount of collected information. The SKA project is managed by the Square Kilometre Array Observatory, SKAO, an intergovernmental organization headquartered at the Jodrell Bank Observatory in the United Kingdom. The collaboration involves countries from 5 continents, including Australia, Canada, China, India, Italy, the Netherlands, South Africa, Sweden, and the United Kingdom. This global cooperation allows the sharing of resources, expertise, and funding, ensuring the success of the project. Construction of the SKA began in 2021, with the first phase expected to be completed by 2029. Once operational, the SKA promises to revolutionize radio astronomy, providing data of unprecedented quality and opening new frontiers in our understanding of the universe. The Square Kilometre Array represents a milestone in astronomical research, combining international efforts, technological innovation, and ambitious scientific goals to explore the depths of the cosmos like never before. Thanks to its unparalleled capabilities, the SKA will not only answer fundamental questions about the nature of the universe but will also open new perspectives for science and technology in the future. Thank you for watching. Leave a like and subscribe to the channel so you don't miss future videos.